Accuracy and Performance Assessment for Transmission Line Models. It's presented by Alireza Masoom. Alireza Masoom is currently a PhD student at Polytechnique Montréal. His research interests are computation of electromagnetic transients using high-level programming languages and high-level methods. Please.
Hi there, I'm so pleased to present you the article titled Simulation of Electromagnetic Transients with Modelica, Accuracy and Performance Assessment for Transmission Line Models. In this presentation, first we have a short introduction on the Modelica. Then the theory of transmission line is briefed, focusing on wideband and constant parameter model. Next, it's explained how we model transmission line using the Modelica language. Afterwards, the results obtained by simulation in open Modelica environment are compared with EMTP. We will speak about the accuracy and performance of our models. At the end, we will go through conclusion. Let us start with the question. What if we could model a physical system as easy as writing its equations on a paper? Yes, it's possible. Modelica is an equation-based declarative language specialized for simulation of hybrid physical systems. Each model is described by equations, as opposed to usual programming languages, or to block diagram representations that commonly employ assignment statements. What does equation-based mean? It means the variables are defined as a function of time. The focus is on differential algebraic equations, which describe our dynamic systems. It allows modeler to concentrate further on defining the models, rather than how the equations are solved. Modelica is a declarative language, in the sense that it defines the facts and relations rather than defining workflow or imperative assignments. It assumes that the algorithm used to the numerical solver will be provided by an appropriate compiler of the language. It's the language duty to sort and optimize these equations, make it causal, and finally convert it to C code and hand it over to the select solver. Modelica is not the only equation-based language, but for sure the best one so far. The language supports the concepts of object orientation, such as inheritance, modularity, and encapsulation. In the procedural and imperative languages such as C and Fortran, compared to declarative ones, it's a programmer that defines the order of assignments line by line. But in Modelica, it's not important where an equation is coded. As a consequence, it's possible to create a causal models. This means models with no predefined input and output relation. Therefore, Modelica gives us more clarity, which is important for pedagogical purposes. Modelica is an open source language. There are many commercial and non-commercial environments such as Open Modelica, Simulation X, Daimola, MapleSoft, and Scilab who support language. Modelica supports FMI, a standard which is supported in much software for the purposes of co-simulation and model exchange. It's a super interesting feature. Okay, let's come back to our application. The dynamic model of a power system is a hybrid differential algebraic equation system, or DAE. The DAE systems contain discontinuities. These discontinuities represent the action of switches and overexcitation limiter in a controller and etc., which may cause the dynamics of some system variables to alter abruptly. One of the main motivations for the use of Modelica in EMT modeling lies on the ability of the language to express hybrid mathematical models. Modelica provides constructs for expressing both continuous and discrete time variabilities. Historically, the EMT tools use the imperative languages, and often differential algebraics are discretized in component level. The solver is usually trapezoidal, Euler, or combination of them, and model and solver are tightly integrated. Modeling of transmission line is one of the most important and most complicated aspects of the power system modeling. For EMT simulations, the most appropriate models are those who consider the parameters distributed along the distance. Equation 1 is the principal equations describing the transmission line in frequency domain. These equations represent the line at each end by a Norton equivalent circuit. The current and voltage in one side of the line is linked by the voltage and current in other side multiplied by the propagation function h. Constant parameter is a simple case in which the impedance and admittance matrices of line is calculated in a fixed frequency, for example 60 Hz. In consequence, the matrices H and YC in equation 2 are frequency independent. However, since the propagation modes cannot be represented at high frequencies, the CP model is only recommended for modeling lines in analysis of problems with limited frequency dispersion. If we apply inverse Laplace transform to equation 1, the equation 4 is obtained with a small computational burden. Wideband or universal line model is considered an accurate model for both transmission lines and cables. The calculations are totally different because in this case the impedance and admittance matrices are frequency dependent, which in turn yields the frequency dependent matrices of H and YC. So using convolution for transforming from frequency domain to time domain is inevitable. Computationally, convolution is a heavy burden job. The basic idea of frequency dependent line models in EMT type programs is to use rational approximation for admittance and propagation matrices. Rational functions allow efficient computation of convolution integrals through recursive schemes. Vector fitting method is a robust numerical technique used to represent the propagation function h and characteristic function yc as a sum of rational functions. Equations 6 and 7 represents the yc and h as a sum of zeros and poles. Vector fitting is not in the scope of this paper, and we go through it. The model can be directly converted into a state space form. This is what we need in Modelica language. Considering terminal K of the line model, equation 8 is rational representation of the product YC-VK, and equation 10 is rational representation of product H times IM plus YC-VM. Now we can calculate the shunt and hyster current in time domain. Equation 9 and 11 provide the basis for the wideband model and are exactly what we use in our modeling in Modelica. It's super interesting, since in conventional EMT tools we need a large amount of codes for interpolation, integration, and change of variables as well. Well, now we are in a good position to show how these models are implemented by Modelica. The schematic of steeple line model is illustrated here. As described earlier, we need two types of calculations. First, calculations related to the history terms, and second, calculations related to Norton equivalent. In Modelica, the input parameters are characteristic impedance, propagation time, resistance, and length of line for single phase, or in modal form for multi-phase line. If the line is untransposed, we have to give the modal transformation matrix as a parameter. Because lack of time, here I just show the codes for wideband model, whose are more complicated. Here, in the right side, we see the schematic of wideband model, exactly what is implemented in Modelica. The parameters of vector fitting are read from EMTP and converted to Modelica readable file directly. Then the shunt current is calculated using equation 9. In this slide, the various parts of Norton equivalent in Modelica are illustrated. You can see here in equation compartment the injected current into the line is the sum of shunt current and hysteresis current. And in the next line, the shunt current is coded exactly as seen in equation 9. The one-by-one correspondence is highlighted here. This slide shows the calculations of hysteresis terms. We can see the same procedure in order to calculate the hysteresis terms of wideband model. Here we can see how the derivative and delay operators made easy the modeling. Well, now we can check and validate our models with EMTP, which is a famous and accurate software EMT domain. In this case study, a 6 conductors 3-phase cable has been simulated. The data of the test are found in EMT examples. Each pole of the switch is closed at a specific time. The voltage curves for conductors and shields at the receiving end of the cable are found here. The dashed black line denotes EMTP results. It's observed that the Modelica curves stick to EMTP bonds exactly. I draw your attention to the CPU time and the relative error norm, which is found here. This is the second test case. We have used IEEE 13 bus network. We know that the network is a distribution network. All lines are untransposed with short length. The loads are unbalanced. So it provides a good example for testing the models coded in Modelica. The scenario is to create a single phase earth fault on bus 6 and 5 here at t equals 60 milliseconds and tripping the line by the CB2 at t equals 160 milliseconds. Let's observe the voltage curves compared with MTP. As you can see in the right side, we see that the Modelica curves stick to MTP bonds in this case as well. In the right side of this slide, the currents passing through the CB2 are compared. We see the same results here. In the left side, an accuracy analysis has been carried out using the results obtained by these solvers, trapezoidal, Dassault, and IDA. Numerically speaking, the table shows that accuracy of modeling with the language is excellent. You can see the figures here. This table shows a comparison of CPU times. The CPU time for Dassault, IDA, which are adaptive solvers, is better than the fixed step trapezoidal solver. However, as you can see here, it's not satisfactory yet in comparison with EMTP. There are many reasons for that, such as optimized solver and using the modified augmented nodal analysis EMTP. Moreover, there are some techniques in way to accelerate the computation in Modelica. Let's wind up our presentation with conclusion. It's been said that Modelica is a powerful language for EMT simulation. The two major electrical elements, I mean the wideband and CP model, are demonstrated here. It's observed that Modelica models are easily readable and understandable, which is super important for pedagogical purposes. We saw how the built-in operators such as derivative and delay can make easier modeling. Since the model is decoupled from solver, therefore, it's possible to switch from one solver to another, which is the native feature. Modelica is compatible with FMI. The feature allows us to co-simulation and model exchange. This is super important because the number of software in supporting the standard is increasing. The computation time is not comparable with EMT type tools, but the future is promising. We believe that there is the opportunity for Modelica EMT simulation of power systems. In this slide, we have marked our future objectives: improvement of performance and developing an EMT detailed library comprising more power electric models, such as synchronous machine and saturable transformer, are of the major of them. Thanks for your attention.
Thank you very much for this presentation. Now it's time to ask questions. I do not see any questions in the Q&A. Any questions, please? There was a question Alireza raised about solvers. Can you comment on the solvers of Modelica?
Yes, hi. Thank you for attention. The solver is, as mentioned in the presentation, the solver is totally decouples the modeling. And we can select a range of solvers, implicit or explicit, the adaptive solvers or fixed steps solvers. It's not important. Of course, it depends on the IDE, the compiler who supports the solver. For example, in the Open Modelica IDE, we can select Dassel, IDA, trapezoidal, Euler, backward Euler, forward Euler. This is available. But in other IDEs, it's not maybe limited. It's an option.
And another question was, is this open source?
Yes, sure. This is an open source language supported by the Modelica Association. It's possible to download the environment, Open Modelica, and it's possible for codes. It's accessible to change, to modify it. It's open source, yes.
Okay, any other question? No more questions. So thank you very much, Alireza. So now we are going to move to the next presentation, passivity